So first quarter, you folks probably did nomenclature, SN1, SN2,
Yep.
E1, E2, yep. Second quarter, probably a lot of alcohol reactions. Does that sound familiar?
Yeah.
Well, this quarter, as you can see, we're doing a lot of aromatic reactions. That's kind of what a large theme of this quarter is. But it really piggybacks on a lot of the stuff that we have been doing, you have been doing with Sean. So a nucleophilic substitution. This is going to be different. It's kind of, I mean, it's not unlike our electrophilic addition or substitution. But a nucleophile, remember, what is a nucleophile once it wants the positive proton? And so we can do that, but you know, before we talked about replacing leaving groups other than hydrogen. Right? That's what this is about. Okay? There has to be 3 criteria though for this to work. And if these aren't met, you're not going to get a reaction. Okay? We have to have a strong electron withdrawing group, so a strong deactivator, like a nitro group. Okay. So if the nitro group is present, check. You also have to have a good leaving group, and you guys talked about leaving groups prior to OChem 3. Halides are good leaving groups, right? So check, check. The last criteria is that they must be ortho or para to the electron withdrawing group. Okay? So here or down here. If they're meta, it's not good. So strong deactivator, good leaving group, ortho or para position. And if any one of those criteria are not satisfied, it's not going to go. Okay? All right. And then this is the mechanism. And you know, it might look similar to electrophilic substitution, right? The main difference is that we have not an electrophile, we have a nucleophile that's attacking. Right? And so, what does a nucleophile do? It adds electrons. That's what it does. Electrophiles take electrons away. And so that's an important distinction to make, because it's going to give us a different group of intermediates here. Okay? We call it the Meisenheimer complex. So not sigma complex. Meisenheimer, because it's different.
Negative.
There's no carbocation, right? It's negative now. With the electrophiles, we're taking. So taking electrons means we create a positive charge. With a nucleophile, we're putting them in. And so they're going to dance around. Okay? And we have these intermediates, these resonance structures coming in. So here is our good leaving group. It's para to our strong deactivator. We bring in a strong base. The base is going to attach here, and now we've donated those electrons, and they're going to dance around here. So the charge goes here, it skips one, goes there. Skips one, goes there. But at some point, we get to this. And this is important, okay? We have the charge on this oxygen, right? Here, it just had the positive and the negative, so it balanced out. There was no overall charge. Positive, negative, but at some point, this nitro group, because it's electron withdrawing, it sops up. It's like a reservoir for the electrons, okay? And that's going to allow this leaving group to take off. And so we're just, it's an elimination addition reaction, right? We're eliminating, or I'm sorry, well in this case it's addition elimination, right? We're adding on our nucleophile, and in its place, or the nucleophile essentially takes the place of the good leaving group. Does that make sense?
So if the electrons are like in the ring, it's going to hold on to that leaving group, but then if it can go to the withdrawing group, it allows it to leave better.
Allows it to leave, yeah.
Okay.
By storing that electron density down in that electron withdrawing group, we can then expel the leaving group.
Okay.
Kick it off.
All right.
Okay. And that's why it has to be ortho or para. Because if it's meta, that charge
Yeah.
is going to be here. And it's going to skip. It's going to skip this carbon.
Yeah.
And so then it can't be a reservoir.
I see.
And so the good leaving group isn't going to go.
Oh, we'll get to that. Okay.
Okay. Does that make sense? All right. Skips past it. So, let's see what we got going on here. We have strong deactivator. We have two, not just one, we have two good leaving groups. And we have our base that we're going to use to attach this. We're going to essentially make an ether here, right? This sodium's going to kick off. We're going to put this molecule onto there. Okay? But where?
For the chlorine is?
Why?
Because it's para to the
Yes.
electron withdrawing.
Yes, remember? They have to be ortho or para. This bromine is meta. So, right, this is going to come here and essentially do that. If it, the bromine, that won't give us the Meisenheimer complex that we need to allow this to be the reservoir for the electrons to then facilitate the leaving. So let me get, oh man, is it, okay. Maybe I've already mentioned this, but is it not infinitely harder to draw a hexagon like this versus with the point up?
I'm the other
Not
way
just
around.
me.
No, I'm a flat
I
top.
hate it when they do this. It's going to look terrible.
It's funny, it's easier one way than the other.
Right? I mean, yuck. Okay, so bromine, we have our NO2, and then our OCH3. Good. Oh, by the way, there's a job fair today. I put an announcement. I don't think it's going to apply to any of you because you're set, Rob, and you know what you're doing, and you're transferring. So But if you wanted to after class, I know that there at some point is going to be, at least they're saying, some mock interviews.
Okay.
So if you ever have another interview, you don't want to be as nervous. You know, maybe that'll help.
Yeah.
I think they also, I heard talk of like a resume clinic or something to help you work on resumes.
That's cool.
Anyway, it's happening today. Free food, definitely. So at least get the free food.
Yeah.
All right. Ooh, I love it. Synthesis. Start with benzene. Using any other necessary reagents of your choice, design a synthesis for this compound. So now think back to that problem, you know, the 2 or 3 slides in, where I was like, okay, we're gonna tack on this, I don't know if it was a bromine or a chlorine.
Yeah.
And I said, okay, yeah, that was like several weeks ago, but this is our starting, you know, basis for then creating what we want to later. Okay. So I'm going to erase this.
Okay.
And I'm going to draw my benzene point up. Anybody remember how we can put a bromine on there?
You need the metal.
Yeah, just the metal,
yeah.
right? And you can
Iron.
You can shorthand it like this. I think that's. Is that how we?
Yeah, I think so.
Yeah. We're essentially going to do this right here. We're just attaching our bromine. Or you can do chlorine. I lost. Here we go. Okay. So that's going to give us something with a bromine on it. Okay, cool. It's a good starting point. What else can we do?
So you can do a para addition or add
We want to get a nitro group on there, right?
Yeah.
So, oh, actually, we haven't done this yet.
Oh,
I mean, I don't think, maybe you talked about this, but actually, let's make this,
okay. Yeah.
let's make this, we'll get to this, right? So actually, the next step, if we wanted to make this, we'd make this first, and then there's yet another reaction that we can replace the nitro group with an amine group.
Okay.
Okay. So for starters, let's just keep it simple. To make this, we need to do that SNAR reaction, right? We need to tack on a bromide, and then we want to put a nitro para or ortho. Now, will that happen? What is this? This is an ortho para director.
Yep.
So when we add a nitro group, it's going to be ortho para. Hey, that's great. It works out, right? So if you remember, how do we do that? How do we add a nitro group? HNO3 and sulfuric acid.
Oh, okay. Yeah.
Okay, so that gives us
Would you also get the ortho product too?
We would.
Okay.
and we get probably twice as much, right?
Yeah, right.
Because there are two positions. So
Yep.
we're going to get a couple of products here. Now, excuse me. Next step, we need to get that sodium hydroxide. We want to put an OH on there. So in this case, we used a base that had this on here. So if we use a base that instead of this
An
has
AOH.
OH, sodium hydroxide would fit that bill. Generically, it's written in the mechanism, I believe, is just
Oh,
this,
okay.
right? But this could be any base. Okay. And then, what else do we need for that? Is it in there? I'll write that in there.
Oh, acid.
We need some hydronium
Hydronium.
um, to donate the protons. 70 degrees, I don't care if you write that on there.
With the
Make it a little warm.
With that hydronium, just it exists naturally, or if you have like base in there, you'd have to add, because like wouldn't that conflict with the base? Or?
That's a good question. I think that that's going to just be in the, because water is amphoteric, so
Yeah.
you're going to have some presence of H3O. I'm not sure if it's just the inherent H3O in there already, or if that's, I'm guessing that's probably denoting an acid at some point, but I'm not, in none of these mechanisms, it's always H3O.
Okay.
So, I'm guessing that is just, that's part of the water that's in the solution.
Okay.
Or you add water and then the H3O in that
Yeah.
is part of the mechanism.
Okay.
Wait, so
But-
what proton needs to be donated to it?
So, essentially we're going to be breaking these off. This is going to dissociate, and then the proton is going to really go to the leftover OHs.
Okay, it's just to
And just
stabilize
form
the
water.
OHs.
Yeah.
Okay.
Nothing, we're not adding anything to the ring.
Right.
Okay.
So then the OH goes here. And then yes, we would also have ortho.
Okay. So could you do like a purification to remove the ortho if you only wanted the para, possibly?
Yeah, and that's that's when we get into trickier things, because the ortho is probably going to be more abundant. But yeah, there are ways to separate that out.
Okay.
And honestly, now that I think about it, it may, again, there's sterics here, right? So we put the bromine on,
Yeah. That's
and
big.
this is a bulky group, so sterics would favor para, even though there are more
Yeah.
ortho positions.
Okay.
So maybe it's 50, maybe it's closer to 50-50 than twice as much. I don't know the answer to that though. All right? How are we doing? Didn't get, can I erase this? Is that good? Didn't get as far as I was hoping. Got a little distracted with those Chem 103 youngins. Chem 103, man, it seems like a lifetime ago, right? A year ago. Well, actually,
It's like
a year ago for you,
it was like 4 o'clock.
COVID, we just blotted that out of our.
It's still been a long year.
So, all right. What else can I get done? Oh, okay. Here's an interesting one. So, I'll go over here. Elimination addition. So we're going to take something off. We're going to put something on. We have a chlorobenzene, and if we put in sodium hydroxide, nothing's going to happen, okay? Unless we add a lot of heat, okay? Then we can override that activation energy and we can replace, eliminate the chlorine, replace it with an alcohol. All right. But it's a little weird because if we were then to take something like this and replace it, now we have the amine group. It's para and meta. Right? That's kind of strange. This right here is orthopara, right? Chloride, that's orthopara. But the products we get are replaced at a para and meta position. What's up with that? Well, turns out that we can do some isotopic labeling. Isotopic labeling, it just means you're using a radioisotope of C14. So kind of like, it's carbon dating technique, right? Only instead of dating something by seeing the ratio of C12 to C14, we can label a specific carbon with the C14 and see where that carbon goes, right? It's a way to follow it. This is how, this is used a lot in biochemistry. Okay, so, has anybody had biochemistry? Do you have that? You probably need it at some point, right?
I do. I'm taking it online.
Okay.
Probably.
Well, you're going to learn a lot. And we'll do a little. I'm going to try and make the second half of this quarter OChem, the OChem side of biochem. So you'll get a little precursor. Since all of you are more, since all of us are more biologically focused, if you look at the OpenStax, there are chapters on carbohydrates, lipids, nucleic acids, and so proteins. So we can incorporate that in this class. But I'm not going to have you guys memorize the Krebs cycle. I'll leave that for you later on. But how did we learn the Krebs cycle? How do we know what it is? And if you don't know what I'm talking about, look it up. It's just this circle with all these molecules coming off of it, and it's, you know, the bane of biochem students' existence. But we know it because we would label sugar with C14, and then look at the process of glycolysis and going into this what is called the Krebs cycle. Right? So it's a very common and not so new technique to figure out where those carbons are going. All right? Excuse me. And so this asterisk is denoting that we have radio-labeled carbon here, C14. Okay? And so we react it, and we end up getting essentially a 50-50 mix of the amine going to the radio-labeled carbon, and then it going to the other side of the radio-labeled carbon.
Ortho or just?
Which makes it, well, depending on if anything's attached, where something is attached. If something was attached here, right, it's para. If it's attached here, it's going to be meta. Okay. So, and I did para both, but you know what I'm saying, right? If it's either going to be para or meta. Why? Turns out that this forms a crazy intermediate called benzyne. Remember, ine is 3 bonds. Okay. So we have our chlorobenzene. We put in our base here. A base accepts the hydrogen, right? That's what bases do. But the hydrogen leaves behind the electrons. Okay. The electrons then go here and kicks off. It makes it, just like we just like we sopped up the electrons to make that leaving group leave, now we're putting it into this bond here. So this has to leave,
Oh,
right? Because there are 4 bonds here. It can't have 5. So we've strong-armed that chlorine off by forming benzene. But benzene is not stable, right? And so here's the radio labeled carbon. All right. Okay. So benzene is going to be around temporarily. And this is a more detailed mechanism. Okay? What's going to happen is the leaving group leaves, right? So elimination, right? Loss of a leaving group. And then we bring in sodium hydroxide or something, and that attacks, right? And then these are sopped up and turned into the hydronium. But just like our alkene reactions, right? You guys remember like hydrohalogenation? If we have an alkene, and we react it with HCl, hydrohalogenation. We're going to break this bond, and something's going to go here, something's going to go here, right? On either side of the bond. Do you guys remember how to know which one?
I think
You guys remember that name?
Oh,
it's like water and chlorine goes on.
Markovnikov.
Markovnikov.
it's like, yeah, that's what it was.
Yeah, Markovnikov addition.
Markovnikov.
Yeah.
Markovnikov's rule is the hydrogen goes wherever there are the most hydrogens,
Yeah.
right? So how many hydrogens are on this one?
1.
1, right? Because there are 3 bonds here.
Yeah.
How many hydrogens are in here?
0.
0. So this will be the chlorine, and this will be the hydrogen. Okay. Similar thing here, right? This is temporary. So this bond is gonna, this alkyne is going to break down, and you're going to tack on that hydrogen on either side of that triple bond. So depending on if you have something here, right, or let's say here, right, there's a chance that the alcohol will go here, and in that case, it's para.
Yeah.
There's a chance that it could go here too. In that case, it's meta. So that's how they figured out that weird, atypical pattern with their synthesis by the radio wave. Okay. Turns out you can also do this with a Diels-Alder reaction. And then you have I learned, so when I taught this last year, I had a student who works in a morgue. And so she told me that there's a difference between a coffin and a casket. So, shoot, I forgot which is which, but one is angled and one is just a rectangle. So this is either, I think this is a coffin. I think
I feel
I feel like that
caskets.
would be cool.
Yeah.
I think caskets are
Less
more
specific.
rectangular.
Yeah.
She was really interesting to have in class. But this is so this is the coffin shape. With this, because we have this benzene, right? One can go up here, and then this goes here, and then we still have the benzene. Kind of weird.
Because sarcophagus, the Egyptians.
A sarcophagus
Yeah.
kind of too, yeah.
So
yeah,
the
definitely.
coffin probably is
We would call it
durable.
sarcophagus so that I don't have to keep track of the coffin casket. All right, well, we're out of time, so this is really just practice. I would like to get into, I'm already like a day behind because I'm 2 days behind from last week and all that. So I don't want to skip over this too much. There are some important roadmaps to making things, right? So this kind of stuff will help you when you have a synthesis problem. If you need to get to a certain destination, put it in your GPS and it says, turn here, go here, right? I was really upset because now Google Maps is putting alternative routes that are like half an hour slower. Like, don't tell me what's, like, if there's something quicker, then tell me that. But don't say, oh, here's a suggested route that's 33 minutes slower. Why would I want to do that? Unless I'm trying to avoid getting home to my
destination.
But anyway,
They know their market.
this is a roadmap, right? It tells you, okay, what do I have? If I have this, or this, I can get to here, and then from there, it's a flow chart. So that'll be helpful. So really, not a whole lot of stuff. So I don't want to skip over this. I will touch on this on Tuesday, but maybe if you could kind of go over these practice problems as homework, then we'll go over it briefly Tuesday morning. All right? Go get some grub if you want to, and have a great weekend.
Oh, is the lab open
Oh, that's right, melting points.
to?
Yes. In fact, Chem 103 should just be wrapping up in there. So,
Is it possible? Do you know if I can do that on Monday? Melting points?
Monday, there is a lab